Hello friends, welcome back. In previous video we have started the carbohydrates chemistry, and in last lecture we have seen the definition, introductory part of carbohydrate, then the classification and the structures for the aldoses, then uh, what are the epimers. Okay, so in this lecture we are going to start the next point, that are the cyclic structures of the monosaccharides or the hemiacetal formation. So the aldoses contain an aldehydic group with a several alcohol group. As we know, if you can see the structure for the glucose, in the glucose the main functional group is the aldehydic group. Okay, and there are several the chiral carbons which are containing the OH group. That means the aldoses contain the aldehyde functionality along with the alcohol groups, and the cyclic form of the D-glucose are the 6-member hemiacetal formed by the intramolecular reaction of the OH group at the C5 with the aldehydic group. That means if you look at the structure for the D-glucose, in the D-glucose there are 6 number of carbons, and the functional group in the D-glucose is the aldehydic group. Okay, that means the carbonyl carbon, and the other 5 carbons are the chiral carbons which containing the OH group. So the 5 number carbon atom which contain the OH group, the lone pair of this OH can attack over this carbonyl carbon of the aldehyde functionality. Then there is a formation of 6-member hemiacetal. Okay, due to the intramolecular reaction. So there is a formation of 6-member hemiacetal. The cyclic structure of monosaccharide are named according to their 5 or 6-membered rings. That means the depending on the structure of this monosaccharide, it will be whether it is a 6-member ring or a 5-member ring. That is a 6-member cyclic hemiacetal called as a pyranose, derived from the name of the 6-member cyclic ether pyrene. The 6-member cyclic ether is called the pyrene, and if the form hemiacetal is the 6-membered, then it is called the pyranose. That means the cyclic structure of the monosaccharide are named according to their 5 or 6-member ring. If the ring is a 6-member hemiacetal, then it is called the pyranose, and if the ring is a 5-member cyclic hemiacetal, then it is called as a furanose. Okay, then and the furanose is a derived from the 5-member cyclic ether furan. So the furan is a 5-member containing oxygen atom. Therefore, if the cyclic hemiacetal form is a 5-member, then it called as a furanose, and if the 6-member cyclic hemiacetal, then it is called the pyranose. For example, the glucose, the form the if the glucose form the cyclic hemiacetal, then the glucose containing 6-membered, then it is called the glucopyranose, and if the 5-membered ring of fructose, then it is called a fructofuranose. So see the reaction. This is the D-fructose. The fructose, in this fructose, this is the second number containing the carbonyl functionality. Okay, and this is the C5 carbon which contain this hydroxy group can attack over this carbonyl carbon, and we got the lone pair of this oxygen can attack over this carbon atom, and here it is the opening of this bond. Okay, so this is the 5-member cyclic acetal, therefore it is called the D-fructofuranose. This is the 5-member, therefore it is called the furanose, and it can be obtained from the D-fructose. Hence here we write the D-fructofuranose cyclic form. So this 6 number carbon contain this CH2OH. Okay. Then this is the 5 number carbon atom is attached to this second number. Therefore this 5 number is attached. This oxygen over this 5 number carbon atom can attack over this carbonyl carbon. Therefore here the 5 number carbon attached to this oxygen, and there is a opening of this O negative, and after the hydrolysis there is a formation of OH. So here we write, here it is a OH and this is the CH2OH. So it can be obtained from the D-fructose, hence we write the D-fructofuranose cyclic form. Then here it is a glucose molecule, okay, and this is the C5 carbon atom. So the hydroxy group over the C5 carbon atom, and here it is a first number of carbon containing this aldehyde functional group. The lone pair over this oxygen can attack over this carbonyl carbon. So here we write this molecule into this type of structure. Only the structural arrangement is different. The molecule is same. Okay. So the lone pair over this oxygen attacked over this. Okay. And here, if the formed OH, that is the after the hydrolysis, here it is a formation of OH group. Okay. So the OH is trans to this oxygen, then it is called alpha. So, and this structure is obtained from the D-glucose. Hence, we write here the alpha D-glucopyranose. Here it is a 6-member ring. Therefore, here we write the pyranose. And it is coming from the glucose molecule. And also the oxygen, this OH group and this oxygen are trans to each other. Therefore, here the name is a alpha D-glucopyranose Haworth projection. This is the Fischer projection and this one is a Haworth projection. But this OH can also be the cis to this oxygen. Hence we write the structure as like this. If the OH and this oxygen is a cis, then it will be the beta D-glucopyranose Haworth projection. So it may be beta D-glucopyranose or alpha D-glucopyranose. Just difference is if it is a trans, then it is a alpha. If it is a cis to this oxygen, then it will be the beta D-glucopyranose Haworth projection. So what are the Haworth projection? The Haworth projection is a flattened diagram used to represent the stereochemistry of carbohydrate. The 6th member ring of D-pyranose is represented as a flat and it viewed edged on. The ring oxygen is always placed in the back right hand corner. In the last structure, we have write the oxygen on the back of the ring on the right hand corner with the anomeric carbon, that is a C1 on the right hand side, and the primary alcohol group drawn up from the back left corner, that is the C5. And the group on the right in the Fischer projection are drawn the down in the Haworth projection. So if you look at the structure, the groups which are right in the Fischer projection, which are right the down in the Haworth projection, and the groups on the left in the Fischer projection are up in the Haworth projection. So here are some molecules which can, here we write in the Fischer projection as well as the Haworth projection. The first one is a alpha D-glucopyranose. This is the Fischer form of alpha D-glucopyranose. This is the 6-member ring. Therefore, here we write the pyranose. This is the Fischer form of alpha D-glucopyranose. And this one is a Haworth projection. So you can see here the oxygen is drawn to the back on the right hand side and the OH is the below in the Haworth projection. This one is a beta D glucopyranose. So the Haworth projection for the beta D glucopyranose is like this. This OH and this oxygen are the same side. Therefore, this is the beta and this one is the alpha. This is the alpha D ribofuranose. Furanose means it is a 5-member ring. So these 1, 2, 3, 4 and this oxygen is a 5. Therefore, this is the 5-member and this is the alpha D ribofuranose. The Haworth structure for this alpha D ribofuranose is like this. This OH is below the plane. Therefore, this is the alpha and this is the 5-member. Therefore, it is a ribofuranose. This one again the beta D ribofuranose. The structure for the Haworth projection is like this. This OH and this oxygen is the same side. Therefore, this is the beta D ribofuranose. So, these are the structures for the sugars in the Fischer projection as well as in the Haworth projection. Here are some examples. The alpha D fructopyranose and the structure for the Haworth projection is like this. This is the beta D fructopyranose. This is the Haworth structure for the beta D fructopyranose. This is the alpha D fructofuranose. This is again for the Haworth projection. This is the beta D fructofuranose and this one is a Haworth projection for the beta D fructofuranose. So these are the Haworth projection for the aldoses in the pyranose and the furanose forms. These are the Fischer projection and these are the Haworth projections. So the D-furanose is viewed edge on with the ring oxygen away from the viewer. So the D-furanose, that means the ring oxygen is away from the viewer. That means this oxygen is a back from the viewer and the anomeric carbon is on the right hand side of the molecule and the primary alcohol group is drawn up from the back left corner. That means the primary alcohol group, this is the primary alcohol group, is drawn up. Here we write the up from the back left hand corner. This is the left hand corner back. Here we write the primary alcohol group and the anomeric carbon is on the right hand side molecule. This is the anomeric carbon is drawn on the right hand side molecule in the Haworth projection of the D-furanose. I hope you understand. Thank you for watching.